Welcome, investigators. Every single day, right in front of our eyes, the world is transforming. I mean, think about it. Ice melts in your glass, a bike chain rusts out in the rain, and milk suddenly goes sour in the fridge. But what's actually happening on a fundamental level? Well, today, we're observing the changes happening all around us, and we're going to learn how to crack the case on what kind of shift they truly are.
In this explainer, we've got a solid lineup. First, we'll look at the world of changes, then dive into physical changes where there's no new stuff, followed by chemical changes where entirely new substances form. After that, we'll check out real-world reactions like rust, and finally, wrap things up with crystallization and a quick review.
All right, part one, the world of changes. We're observing everyday phenomena. Let's get right into it.
Section 2, physical changes. No new stuff. We're focusing on form, not identity.
So every single day, substances are changing all around us, and science basically divides these events into two main suspects. Let's look at suspect number one. To really get what a physical change is, you first have to understand physical properties. These are just basic characteristics, shape, size, color, and state, like whether something is a solid, liquid, or gas. So here's the golden rule. A physical change is literally just a change in those specific properties. No new substance is ever formed, and usually you can totally reverse it.
If we open up the case files, you can see this in action everywhere. Imagine cutting a piece of paper into smaller squares. Sure, the size and shape are different, but hey, it's still just paper. Same thing goes for crushing a piece of chalk into fine dust. You could literally add a little water, roll it back into a stick, and let it dry. Melting solid ice? Just pop that liquid water back in the freezer to reverse the whole shebang. The material might look completely different, but fundamentally, its identity hasn't changed one bit. Moving on to Section 3, chemical changes. Entirely new substances. This is when things get transformative. Now, you're going to want to keep this cheat sheet in mind as we investigate. While physical changes are just about altering appearances, a chemical change is a full-blown transformation where one or more entirely new substances are formed. And because the actual identity of the material has been completely altered, these changes are generally irreversible. I mean, you can't unbake a cake, right?
Just think about a burning magnesium ribbon. If you've ever seen a teacher do this in a lab, bring a flame to that thin strip of metal, you know it burns with this brilliant, almost blinding white flame. But here's the real kicker. Once it finishes burning, it leaves behind this powdery ash. That ash looks absolutely nothing like the shiny metal we started with, and that's because it's a completely new substance called magnesium oxide.
Here's another really cool clue. If you dissolve copper sulfate into a beaker of water, you get this gorgeous blue liquid. But if you drop an iron shaving blade into that blue copper sulfate and wait about half an hour, the liquid magically turns green. Actually, scratch that. It chemically turns green because a brand new substance, iron sulfate, has formed. Plus, if you pull the blade out, you'll see this brown deposit all over it. That's pure copper. Entirely new substances, completely different colors. You can kind of think of these chemical changes like math equations, where your starting materials, which we call reactants, combine to equal entirely new products. So magnesium plus oxygen equals magnesium oxide ash. We just saw how blue copper sulfate plus iron yields green iron sulfate and brown copper. And if you mix vinegar and baking soda, you'll actually hear a hissing sound as they react to form carbon dioxide gas. You can even pass that invisible gas through lime water, and it turns the water milky white because it creates calcium carbonate.
So, as a change detective, how do you actually spot a chemical change in the wild? Well, your primary clues are all sensory. Look for unexpected heat or light, just like our burning magnesium. Listen for a fizzing or bubbling sound, like that baking soda and vinegar. Notice if there's a sudden color change, if a strange new smell is given off, like when food goes bad, or if a brand new gas is suddenly bubbling up. Section 4, real-world reactions and rust. Let's talk about the cost of chemistry.
Because chemical changes aren't just fun little lab experiments, They happen out in the real world with massive consequences. Honestly, our survival depends on them. The digestion of food in your stomach, the photosynthesis that plants use to make their food, even the protective ozone layer way up in the atmosphere that absorbs harmful UV rays to shield the Earth, these are all continuous, absolutely crucial chemical reactions. But they can also be everyday annoyances, like food spoiling and smelling awful, or a freshly sliced apple turning brown when you leave it on the counter for too long. And that brings us to how destructive chemical changes can be. Just think about rusting metal. Rusting happens when iron reacts with oxygen from the air and water,
which can literally just be moisture in a humid environment. It creates iron oxide, also known as rust, and this process slowly but surely eats away at iron bridges, ships, trucks, and park benches, destroying their structural integrity. The sheer monetary loss to society just from rusting iron is absolutely staggering.
But hey, good detectives always look for a solution, right? To stop this destructive chemical change, we use a brilliant process called galvanization. Since rust needs both oxygen and water to attack the iron, we simply block them from getting there. By depositing a protective shield of a metal, usually zinc, over things like iron-water pipes and ship holes, we create a physical barrier. The oxygen and water can't reach the iron, and the rusting is stopped right in its tracks.
Section 5. Crystallization and Review. Time to extract the pure truth. Let's close out our investigation with a fascinating laboratory process that's going to test everything we've learned today. We can actually extract pure substances from solutions using a process called crystallization. Here is how it goes down. You take a cupful of water, add a few drops of dilute sulfuric acid, and bring it to a rolling boil. Then, you slowly stir in copper sulfate powder until the water simply cannot absorb even a tiny bit more. You filter that hot solution and then you wait. You let it cool down completely undisturbed. And over time, beautiful, large crystals begin to form at the bottom. The result is just gorgeous. Look at those large, pure crystals of copper sulfate. I mean, we started with a basic powder dissolved in water and ended up with these massive, geometric, solid structures.
So, detective, put on your thinking cap for a second. Based on the rules we established earlier, what kind of change do you deduce crystallization to be? Remember, we started with copper sulfate and we ended with copper sulfate. No entirely new substance was created, right? Only the size, shape, and state were altered.
Boom! That is exactly right. It's a physical change. This brings our entire investigation completely full circle, right back to our first suspect. Even though the visual transformation from a cloudy hot liquid to a giant blue crystal looks super dramatic, because the fundamental identity of the substance stayed exactly the same, it is strictly a physical change.
Well, you now have the tools to analyze the world around you. The next time you're in the kitchen cooking up a meal, really observe it. Feel the heat, listen to the sizzling sounds, smell the aromas, and watch how the colors shift. Ask yourself, what kind of change is happening right in front of me? Thank you so much for joining me on this investigation. This explainer was created by Ramesh Kumar Jha. Keep observing and stay curious out there.